Everybody, so welcome to our next video in thermochemistry, which is going to be quite a bit shorter than the last video, hopefully. But it's all about heat transfer between two different systems within one single system. So one lab that we are going to do is we are going to measure the specific heat of three different metals. And we're going to do that using a calorimeter. And we've talked a little bit about how calorimeters work in the last section. So that's when you have your change in temperature, and that's able to tell you how much heat was absorbed or evolved in that reaction. But how do we find the specific heat for the metal in a calorimeter experiment? And there's something that's super crucial that we have to remember when we're dealing with thermochemistry. And the fact of that is that the heat lost in one part of a system is equal to the heat that's gained in another part of a system. So for example, in that lab that you are going to do, to measure the specific heat of a metal, you're going to heat that metal up to about 100 degrees Celsius. You're going to submerge it into water that's at room temperature. And you're going to measure what was the temperature change after I submerged that hot metal into that water. Well, water has one specific heat and the metal has another specific heat. So how do I do that? Well, here's a nice little picture. So I have some hot metal that I'm submerging into a sample of cold water. So this right here, let me get the pen out again. This would be some cold H2O. So it says cold right there. So I'll write cold H2O. And this right here would be a hot metal. Okay. When we talk about heat transfer, the heat is always transferred from the object with the higher kinetic energy to the object with the lower kinetic energy. So when I submerge this hot metal into this cold water, notice how this starts to become less hot. Heat is being transferred from the metal to the water in this process, right? Until eventually the two of these become the same temperature. So these are at the same temperature. What we have to remember is that the heat that's lost by the metal is equal to the heat that's gained by the water. So we can do this by determining, okay, well, if I know the change in temperature of the water, I know the specific heat of water, and if I know the mass of the water, you can determine what is the heat that the water is absorbing, right? So the heat that the H2O absorbed, you could calculate using all of water's values, right? The change in temperature for the water, the specific heat for the water, and the mass of the water in the sample. And if that heat that the water absorbed, since it's getting a higher temperature, your Q is going to be a positive value in this case. But the water is only going to gain whatever the metal gives to it. So the heat is going to be the same. So Q is the same value, but the heat that the metal lost, so the heat that the metal lost is going to be the same value of Q, but it's going to be a negative Q. And that's because whatever heat was transferred from the hot object to the cold object, one is absorbing that heat while the other one is losing that heat. So let's say Q is 50, right? Let's say the water absorbed 50 joules of energy. That must mean that the metal released 50 joules of energy. So Q would be negative 50 in this case. And I would set that equal to the mass of the metal times the specific heat of the metal times the change in temperature for the metal as well. And you can calculate C from that. What's the specific heat? And you're going to do a lab just like this. This is a very common chemistry lab, not just in high schools, but also in colleges. I mean, knowing that heat lost equals heat gained using Q equals MC delta T is really important in thermochemistry. Rather than talk about this, let's just do some example problems together because I think it's easier to do a problem than it is to talk about how to do a problem. So let's go ahead and do it. Sample problem 4 and 5 in your notes together. So let's take a look at sample problems 4 and 5. And sample problem 4, we can look right at this image right here, because I think looking at this will help us to answer this particular question. And this is very similar to what you're going to be doing in that specific heat of metals lab. It's the exact same process. So a 5-gram sample of a metal was heated to 100 degrees and then plunged into 100 grams of water at 24 degrees. The temperature of the resulting mixture became 28. So we took this hot metal, we put it in water, and we know the mass of both of those samples, and we know the initial temperature, and we also know the final temperature for both of these. So 28 is TF for both the metal and the water. So I'll just put here metal and water. I have the mass of the metal and mass of the water too. Anyway, how much heat did the water absorb? So we are going to use Q equals MC delta T, because we're going to have to use that for most of these thermochemical equations. Like I said, that's like the big equation that you need to know. This is like your PV equals nRT for this unit. So we'll use Q equals MC delta T again. And let's figure out Q for the water. So we have to look at all of the variables just for water in this case. So the mass of the water is 100 grams, right? It's telling me that value there. So, oops, okay. We have 100 grams of water. The specific heat of the water, which, because we're working with water, it's always going to be 4.184. Delta T, so my final temperature is 28, like we said, because the water rose to 28. But we're bold there. And we'll subtract from that the initial temperature of the water. So before the metal was plunged into the water, the initial temperature was 24. So I'll subtract 24 from that. And if you calculate this correctly, you should find that Q is equal to positive 1,670 joules. So the water absorbed 1,670 joules of energy when this hot metal was put into it. Whereas the next question is, well, how much heat did the metal lose? Well, if I look back at this, remember, heat lost is equal to heat gained. So if the water gained 1,670 joules of energy, that must mean that the metal lost 1,670 joules of energy. So you don't even have to do a calculation for that. All we need to know is the sign, because the metal transferred that much energy to the water. So B, I'm just going to change the sign for that value. And that's because heat lost is equal to heat that's gained. So knowing that, what's the specific heat of the metal? So we're going to solve for C in this case. So again, we're going to use Q equals MC delta T. But in this case, we're going to use all of the values for the metal. So Q now is negative 1,670 joules. I'm going to set that equal to the mass of the metal. So the metal was 5 grams. So I have 5 grams. I'm going to solve for C, because that's what I'm trying to find. Final temperature of the metal is the same as that for water, because when they were put into one another, they both reached 28. But the initial temperature of the metal was 100. So notice how this delta T variable is a negative, which is why with Q, oops, I forgot a 0 there. With Q, because that's a negative, for C, you're going to end up with a positive value. So make sure that your values for C are always positive and your values for mass is always positive. And if you solve that correctly in your calculator, you should get 4.64 joules per gram degrees Celsius. And that's it. So it's nothing new. We already talked about Q equals MC delta T. And now we're just introducing this fact that heat loss is equal to heat gained. So we just have to change the sign for that Q in order to solve for the specific heat of the metal, which is what we just did. Sample problem 4 is not really, or sample problem 5, I'm sorry. Sample problem 5 is not necessarily using that particular, heat loss is equal to heat gained, but we could, of course, still answer these anyway. So consider the substances in table 1. Which substance requires the largest amount of energy to raise the temperature of 15 grams of that substance from 15 to 37? So let's look at table 1 here. Which substance requires the largest amount of heat? So here's table 1, back in the notes. Well, if we're talking largest amount of heat, there's really only 2 values that we could look at. Let's try to identify the highest specific heat and the lowest specific heat, because it's got to be either the highest or the lowest. Looks like here your water is the highest, right? Liquid water, because its specific heat is 4.184. And if I look at my lowest specific heat, it looks like it's a tie between gold and lead, right? Well, if I want to raise the temperature of something, which one of these, is it gold or lead, either one of those, or liquid water, which of those requires the most amount of heat to raise the temperature of 15 grams by 15 to 37 degrees Celsius? Is it the higher specific heat or the lower specific heat? Well, because water has a very high specific heat, it takes a heck of a lot of energy to raise the temperature of a sample of that. So our answer has to be water. It takes a lot of energy to raise the temperature of water, 1 gram of water by 1 degree Celsius. So your answer for this one is water. And that's because it has the highest specific heat. Water, oops. And we'll say it has the highest specific heat. It takes the most energy to raise the temperature. And then it wants us to actually calculate it. So we'll use Q equals MC delta T, where Q is equal to the energy, or heat rather. Mass of the sample is 15 grams. Of course, you're going to end up memorizing this number, not because I want you to, but you're just going to see it so often for water. And I'm raising it from 15 to 37. So 37 is my final temperature, and 15 is my initial. Calculate that guy correctly. You have positive 1,380 joules. Then for B, it says, which substance in table 1 has the largest temperature change? So which one of these has the biggest value of delta T when 550 grams of the substance absorbs 10.7 kilojoules of energy? So which has the largest temperature change? So let's go back to table 1 and just take a look at these values. It looks like we'll have to analyze between this highest and this lowest value, again, because we want to know which one has the largest temperature change, that largest delta T. So which one of these, when you input 10.7 kilojoules of energy, would the temperature raise the greatest? And your answer is going to have to be gold or lead. It doesn't take that much energy to raise the temperature of gold or lead. So if I input so much energy, the temperature of lead and gold is going to go up much higher than that of, let's say, anything else on here, really. And that's because its specific heat is lower. It does not require as much energy to raise the temperature. So if I put energy in, my final temperature for each of these is going to be the highest. So your answer for B is going to be copper and lead, for really the opposite reason as the first one. Copper and lead. Some days I don't write on here very well, but other days it does good. I'm not sure what happens. It's got the lowest specific heat. So then it's asking us actually calculate that temperature change. So again, we're going to use Q equals MC delta T, but I know Q in this case, Q is 10.7. Notice that this is in units of kilojoules, so I am going to convert this to joules by just moving the decimal place over 3 times. The mass is 550 grams. The specific heat is the same for both of them, so it doesn't matter because they'll both end up the same temperature. And we just want to calculate what's the delta T. It's not asking us for a final, like an exact final temperature. It just wants to know what's the change in temperature. So I'm just going to calculate delta T. And if you calculate that correctly, you would find that your temperature would go up 151 degrees Celsius. So let's say your initial temperature is 100 degrees Celsius. Your final temperature would be 251 degrees Celsius. It's going up 151. Let's go ahead and talk about thermal equilibrium next. And this brings us to thermal equilibrium. So I mentioned thermal equilibrium, I think on one of the previous slides, where the temperature of two objects becomes the same after a certain period of time. The object with the higher kinetic energy transfers its heat to the one with the lower kinetic energy until they are at the same temperature. We say that when they've reached the same temperature, they've reached a thermal equilibrium. And that's the point at which two substances that are in physical contact no longer exchange heat energy. And that's because they're at the same kinetic energy. So if I put out a hot cup of coffee, right, that hot cup of coffee is not at thermal equilibrium with its surrounding environment because that coffee is releasing energy to warm up the surrounding environment. You've reached a thermal equilibrium when they are the same temperature, and that's because that hot coffee has released all of its energy either to your hand or to the surrounding air. So for example, if I have two blocks that are at two different temperatures. So we'll say here block A has a higher temperature than block B. So in this case, block A also has a higher kinetic energy. Higher kinetic energy. This block with the higher kinetic energy, that energy is transferred once they touch physically, gets transferred from high amounts of energy to low amounts of energy. In AP Bio, you might have talked about osmosis and I don't remember what it's called, but it's always from an area of high concentration to an area of low concentration. It's the same for thermal equilibrium. Area of high kinetic energy to an area of lower kinetic energy until they're the same. And then the two blocks eventually will become the same temperature until, of course, that heat flow stops. So here, there's no more transfer of heat that's occurring between the two because we've reached here what's known as that thermal equilibrium. So this right here, I'll just write, we've attained thermal equilibrium. I always think chemistry has like cool band names. Thermal equilibrium sounds like it would be a cool name for a band. So let's think about this right here. You add some cold milk to a coffee, right? And why doesn't the hot coffee and the cold milk, why don't they reach the average of the two temperatures? Well, it also depends on the mass of each sample as well. How do I figure out what would be the final temperature of a large sample of hot coffee and a small sample of cold milk? Remember, heat that's transferred is equal to the heat that's absorbed from the other. That hot coffee is transferring heat to the milk, right? So, and that's because the coffee is very hot and the milk is very cold. So I can calculate, all right, well, how much heat was transferred to the milk? And I could do that by finding the change in temperature of the coffee, right? The initial temperature of just the coffee minus the temperature of the mixture. Delta T is not going to be very large here because normally your amount of coffee is much greater. So the temperature is going to be much closer to that of coffee at the end. Times the specific heat of the coffee times the mass. And because that coffee is releasing energy to raise the temperature of the milk, Q is going to be negative. But remember, the heat that the coffee releases is equal to the heat that the milk absorbs. So my MC delta T for the milk, the mass of the milk, times the specific heat of the milk, times the change in temperature of the milk is equal to a positive Q. But remember, Q is the same value. Whether or not they're positive or negative, it's the same number. So to get these to equal one another, what I can do is to make this Q positive by making this whole side of the equation negative, right? So that means that positive Q equals positive Q, and I could set these whole things equal to one another. So the change, the MC delta T portion for the coffee, negative MC delta T, I should say, negative MC delta T for the coffee is equal to positive MC delta T for the milk. And this is how I could find what is the final temperature for this particular system. If I have two different masses of objects, if I have two different specific heats, and if I have two different starting temperatures, the final temperature is the same. So what is that final temperature of when two objects of different temperatures come into contact with one another? You could do that again using Q equals MC delta T, but it's a variation of Q equals MC delta T. And we have to know that the heat that's absorbed is equal to the heat that's released. And if those values of Q are the same, the absolute values of Q, I could set one of these equal to a negative, and I could solve for a thermal equilibrium. So what is the thermal equilibrium when two objects come into contact? Let's go ahead and do the next sample problem together in the notes. So let's use that Q equals MC delta T, that variation of the equation from above. So we're going to use negative MC delta T for one of these variables, whichever one is losing the energy. And we'll set that equal to positive MC delta T for the one that's gaining that energy. So we want to know what is the final temperature for this system. So a 65-gram piece of iron at 525 degrees Celsius is put into 635 grams of water at 15 degrees. What is the temperature when this system reaches thermal equilibrium? So let's consider which in this system, the iron or the water, is going to have the positive and negative Q. So I'm just going to write down here iron, and then I have water. Because that water is so hot, it's transferring that energy to the water, right? So the energy is going from this hot iron to that cooler water. So your Q in this case is going to have to be negative. That's going to be what's losing the heat. Whereas your water is gaining that heat. So Q is going to be positive for water in this case. Now remember, whatever the iron lost is equal to whatever the water gained. So Q is the same value, which is why I can just manipulate that equation a little bit and say that negative MC delta T for the iron, so this is for iron right here, is equal to positive MC delta T for the water. The reason why I made this side negative is because that would make the value of Q exactly the same without the negative. So I do have to transfer that negative over to the other side to get them to equal. And we can go ahead and plug in all of these numbers to calculate what's that final temperature, because it's going to be the same for both of them. Let's focus on iron side first here. So negative. Looks like my iron is 65 grams. If you look back at table 1, you'll see the specific heat for iron. It's 0.449. And delta T. So my final temperature is what I'm trying to find. And my initial temperature is that 525 degrees Celsius. So 525 degrees Celsius. That's going to be this whole side of the equation right here. This is all my information for iron. Let's go ahead and do the same thing for water on the other side. So the mass of water is 635 grams. Specific heat for water is 4.184. Final temperature is the same because that's what thermal equilibrium is. So it has the same exact temperature. So TF is the same for both. And looks like the water's initial temperature is 15. The most annoying thing about this whole thing is solving this. And even sometimes for me, I try to solve this way too fast, and then I end up getting them incorrect. So I will walk you through very quickly how I solve this one. What we have to keep in mind is that this whole thing right here is negative. So really, I'm going to put this whole thing in brackets because this whole entire thing would have a negative sign. What I like to do first is this times this. So I'm going to do 65 times 0.449. And when I do that, I'm going to keep that negative on the outside, put that in brackets. I get 29.19. And I'm going to keep this variable here. I'm going to eliminate my units just because it makes life a little bit easier. I'm going to set that equal to, again, I'm going to multiply 635 by that 4.184. And I get 2,657. And I'm going to keep TF minus 15. What I like to do next is I will distribute. So I'm going to distribute this into this. And then I actually distribute that negative as well. So when I do that, 29.19 times TF gives me that, but I'm going to keep that negative there as well. So it's negative 29.19 TF plus 15,325 is equal to, and I'll distribute this side as well, 2657 TF minus that number times 15, which is 39,855. So I'm just kind of taking my time walking myself through the algebra here. Got to get the TFs together. So I'm just going to do a little switching here to kind of simplify this a little bit more. I get 2686 TF, and that's equal to 55,180. And if you solve for your final temperature, you'll see it's 20.5 degrees Celsius, which makes sense, right? I have a pretty small, hot piece of metal, and I plunge that into some water at 15 degrees because water-specific heat is so much higher that, and because there's a larger sample of water, that final temperature is not going to be much greater than 15. So 20.5 makes quite a bit of sense when you consider this. These take a bit of practice. We're going to do some of these in class as well. Like I said, if you could set this up, I think putting the values in is the easy part. It's almost going through this algebra that can be kind of a pain in the neck. As always, if you have any questions, make sure you let me know. Take some notes in your note packet, and we will talk about it in class the next time I see you. I hope you have a wonderful day, and I will see you in the next video, which is all about the energy of phase changes. Bye.